Okay, so in this video, we're going to talk about Newton's second law for rotation. Okay, so we spent a lot of time talking about Newton's second law last semester, our beloved F net equals ma. Okay, so that's Newton's second law for linear motion, but there is a rotational version of the second law, and the rotational of the version of the second law looks like this. Okay, so the linear version, we have F net equals ma, and the rotational version, because as we saw in Unit 5a, basically everything we ever learned last semester, we have an equation for it in rotational stuff. All we have to do is make the appropriate changes. So instead of force, the rotational version of force is torque, which we spent a lot of time calculating torque. Okay, so we should know how that works. For static equilibrium, we have the condition that the net torque is equal to 0. But you don't have to have a situation with static equilibrium. You can have a situation where you have a net torque, in which case the object is going to rotate. Okay, and so if it rotates, instead of having linear acceleration, you're going to have angular acceleration, which we've seen angular acceleration before. That's going to be alpha. But what is the rotational version of mass? Okay, so the rotational version of force is torque, and the rotational version of acceleration is rotational acceleration or angular acceleration. The rotational version of mass is what we call I, okay, capital I, and this is what's called the moment of inertia, okay, moment of inertia, okay, or sometimes you'll see this called rotational inertia, okay, and so just to give you an idea of what does moment of inertia represent. So if mass tells you, basically, if you apply a force to something, mass kind of tells you how difficult is it to make something accelerate given a specific force. Okay, so moment of inertia basically tells you, or gives you an indication of how difficult it is to get something to rotate if you apply a torque. Okay, and so in the next video, we're going to do more calculations with Newton's second law for rotation. But for right now, let's see how do you actually calculate moment of inertia. Okay, so pause it there if you need to add that to your notes. Okay, and we can go on to the next slide. Okay, so a few things you need to know about moment of inertia. Okay, so like I said before, the symbol for moment of inertia is a capital I. Okay, the units for moment of inertia is kilogram meters squared. Okay, not kilogram per meter squared, kilogram meter squared. Okay, so kilogram times meter squared. It is a scalar. And again, what moment of inertia basically tells you is how hard is it to get something to rotate. In other words, if mass is a measure of inertia, that tells you how hard an object resists changes in motion. Moment of inertia basically tells you how much does an object resist angular changes in motion. Okay, so in other words, if you want to take something, if you want to spin it around, if you want to rotate it, some objects are easier to start to spin than others. Okay, and so that has to do with moment of inertia. Okay, so what we're going to do now is see how do you calculate moment of inertia for single individual point masses and then also for bigger objects. Okay, so I'm going to go to the next slide. Okay, and so what we're going to do is we're going to see how to calculate the moment of inertia. Now, generally speaking, the equation to calculate the moment of inertia for any object is basically you do a sum. Okay, so that means you add up mi times ri squared. Okay, in other words, you take an object, you break it up into pieces. How many pieces you have depends on the situation. Okay, for each piece, you multiply the mass times r squared, where r is basically the distance from the pivot point, which we've seen before because when we calculate torque, we have RF sine theta. Okay, so R represents the distance from the pivot point, and you basically do m times r squared for however many masses you have in this situation. It could be 1, it could be 2, it could be like a bajillion, it doesn't matter. Okay, now normally if you have objects made up of like millions of tiny little masses, that's normally where you would have calculus and you would have integrals involved. Okay, what we're going to start off with is how do you calculate the moment of inertia for single point masses. Okay, so in other words, if I have one single mass, how do you calculate the moment of inertia for one single mass? Well, if you only have one object here, this is not really a sum. This would just be m times r squared. Okay, so again, m would be the mass and r would be how far away is that from the pivot point. Okay, so let's take a look at some examples. I'm going to erase this. Okay, this is just kind of like a fact slide about moment of inertia, or as it says in the notes, rotational inertia, it's the same thing. Okay, I will put some links that go to some videos just so you can visually see what moment of inertia looks like visually. Um, but if you take a look at the slide here, what we can see is we have two weights on a barbell. Okay, and the two weights on the barbell, if you want to calculate the moment of inertia, it depends on kind of where the pivot point is. Now, when I say pivot point, really the term I want to use really is called axis of rotation. And the axis of rotation is basically like if you imagine something rotating or spinning, what is the imaginary line that is rotating through? Okay, so in the picture on the left, imagine we have these two weights and we have a barbell, and imagine we have like a we somehow drill through the metal bar and we put another bar here and we spin the whole thing so that the weights are spinning around this pole. Okay, so in this situation, if we wanted to calculate the moment of inertia, the equation for moment of inertia says we do the sum of mi times ri squared. Okay, but in this situation, we are adding up two masses because we have a mass here and we have a mass here. Okay, and so what would we be adding? Well, we have m, because that's what the mass is, times r squared plus m times r squared, which would be 2m r squared. Okay, what we have here is we have m times r squared because remember little r represents the distance from the axis of rotation, which in this case, little r is equal to big R. Okay, now in the picture on the picture on the right, what they've done is they've basically changed the axis of rotation. So now the axis of rotation is now here. So in other words, you're basically imagine you grab the left end of the barbell and then you swing it around in a circle, holding onto the left side. So instead of rotating about the middle, it's rotating about one of the masses. And so because the axis of rotation is shifted, when you do the calculation, as you can see right here, the way you calculate moment of inertia is different. Okay, and so you actually end up with a different moment of inertia. So mass and moment of inertia are kind of similar to each other, but moment of inertia is more complicated because it actually depends on where are you spinning the object around. Okay, whereas mass is mass and mass doesn't change. Moment of inertia changes based off of where is your axis of rotation. Okay, and so that's just kind of what a simple calculation of moment of inertia would look like. Okay, now for a single point mass, to calculate the moment of inertia for a single point mass, again, point mass, the moment of inertia equation is just m times r squared. Okay, so what if you don't have a point mass? What if you have like a big giant object? So I said before, this is normally where calculus would come in. Fortunately for you guys, you don't actually have to use any calculus for this class because most of the more common objects, you actually are given the moment of inertia. Okay, it's on your formula sheet. If you look on the formula sheet, they give you the moment of inertia for different common objects. I will show you some on the next few slides. Pause it here if you need to add any of this to your notes. Okay, but just to give you an idea of what I mean, most of these have already been calculated for you. So, for example, if you have like a hoop rotating about a cylindrical axis, the moment of inertia for a hoop would be I equals mr squared. Okay, what if you have, let's say, a solid cylinder or like a disk spinning about its central axis? Then the moment of inertia for that shape would be r squared divided by 2. Okay, and so a lot of common geometrical shapes already have moment of inertia for them calculated. All of the ones that you guys will need for your problems, like I said, are given to you on the formula sheet. Okay, and so We will use this one here in just a second when we do an example, but just to go to the next slide and show you some other ones, we have a solid sphere. Let's say you have like a solid sphere and you stick a pole down through the middle and you spin the sphere around, then the moment of inertia would be 2/5 times mr squared for that object. And again, as far as where those values come from, you don't need to know that because they've been calculated for you. But generally speaking, to actually do the calculation would require calculus. Okay, and so like I said, you don't need to know where those values come from, but you do need to understand how to use them in problems. Okay, so we'll just do a few more examples before we move on. Okay, so take a look right here. Okay, so right here we have example 1, and it says a 25 kilogram child stands on a distance r equals 1 meter from the axis of a rotating merry-go-round. The merry-go-round can be approximated as a uniform solid disk with a mass of 500 kilograms and a radius of 2 meters. Find the moment of inertia of the system. Okay, so first things first, the moment of inertia of the system basically is the moment of inertia of two separate things. First, we have the moment of inertia of the child, plus we have the moment of inertia of the merry-go-round, okay, which it says in the question can be approximated as a uniform solid disk. Okay, so what I would do is I would go to my formula sheet, or in this case, I would go back a few slides, and I would find the equation for a solid disk that is rotating about a cylinder axis, and I would see that the equation is I equals mr squared divided by 2. Okay, that's not something I would memorize, that's something I would look up on the formula sheet. Okay, so for the merry-go-round, merry-go-round, I'm just going to say I merry, the equation is going to be mr squared divided by 2. Okay, so I would do the mass of the merry-go-round, which is 500, times the radius of the merry-go-round squared, so 2 squared divided by 2. Okay, and so that would give me 1,000. And remember, the units are kilogram meters squared. Okay, that would be my I merry-go-round. Okay, so what about the child? Well, it doesn't say anything about the shape of the child, and so I think we have to assume, for the purpose of this question, that the child can be treated as a point mass. And remember, the moment of inertia of a point mass is just going to be mr squared. So basically we have mr squared for the child, plus I merry-go-round, which was m big R squared divided by 2, which we've already calculated and we know is 1,000. So what is the moment of inertia for the child? That would be mr squared, so that would be 25 times 1 squared. So remember, r represents how far that point mass is from the axis of rotation, okay, which in this case is 1 meter. And so that for the child, it would be 25 kilogram meters squared. Okay, so what is the moment of inertia of the entire thing? That would be 25 plus 1,000, which is 1,025 kilogram meters squared. Okay, and that is how you calculate the moment of inertia uh, for a system where you have more than one object. Okay, so in this case, we have two different objects. We have to find the moment of inertia of each one and then add them together. Okay, so remember, if you have a point mass, the equation is always going to be mr squared. If you have a shape like a sphere or a disk or a cylinder or a rod or anything like that, look at the formula sheet. There's probably a moment of inertia equation for that shape on the formula sheet. Okay, so pause there if you need to finish looking at that example, but that's basically a full worked out example calculating moment of inertia. Okay, and then on the next slide, you can see the work written out for the question we just did. Okay, and so even though we started talking about Newton's second law for torque, I'm actually going to come back to that and talk about that in the future. For now, I want to show you some more ways that we could use moment of inertia with other concepts. Okay, and so add this into your notes. What we're going to talk about now is how to calculate rotational kinetic energy. Okay, and so last semester we saw normal kinetic energy, Ke equals 1/2 mv squared. Okay, so you have 1/2 times the mass of an object times its speed squared, and that would be what I would call the linear um, kinetic energy of an object. Okay, now as we've seen so far, in all of Unit 5, basically everything we talked about last semester has a rotational version to it. Okay, and so the rotational version for kinetic energy, the equation looks like this. Okay, and so you see we have 1/2. Instead of mass, we have moment of inertia, because remember, I is the rotational version of mass. And then instead of v, we have omega, right? So instead of v squared, we have omega squared. So instead of linear velocity, we have angular velocity, which makes sense. Now, rotational kinetic energy, of course, is measured in joules, like energy always is. And this is basically the energy an object has just because of the fact that it is spinning. Okay, and so what we're going to talk about for the rest of this video is we'll see what that looks like as far as calculations go. Okay, so I'm going to go on. Okay, so here you can see the side-by-side comparison of rotational kinetic energy and linear kinetic energy. Okay, and so let's take a look at an example. Okay, and this is a question from your quest homework. Okay, so what we're told is the center of mass of a pitched baseball, it should say of radius. Okay, so pitched baseball of radius 5.14 centimeters moves at 54.5 meters per second. The ball spins about an axis through its center of mass with an angular speed. Okay, so this is going to be omega of 93.8 radians per second. Notice, by the way, radians per second is the SI unit for omega, so we don't have to do any unit conversion there. The question asks us to calculate the ratio of the rotational kinetic energy to the translational kinetic energy. Anytime you see translational, think linear. Okay, so translational kinetic energy and linear kinetic energy are the same thing. That's just going to be 1/2 mv squared. And then the last sentence says treat the ball as a uniform sphere. That part is important because what we can do is we can go look at our formula sheet and we can look at different moments of inertia and see that if you have a uniform sphere spinning about its center, the moment of inertia is going to be I equals 2m r squared divided by 5. So in other words, 2/5 mr squared. And look at your OnRamps formula sheet. You'll see that exact same equation is on your formula sheet. Okay, and so let's do this calculation. So first of all, I'm going to open up a new slide. Okay, and let's start by writing down some of our givens. Okay, so what we have the radius is 5.14 centimeters. Okay, so I'm going to write down r equals 5.14 centimeters. In the back of my head, I'm thinking I need to convert that to meters. Okay, so I better not forget to convert that. And it moves at 54.5 meters per second. Okay, so this is going to be my linear velocity, 54.5 meters per second. I also know that it spins about an axis through its center of mass with an angular speed of 93.8 radians per second. Okay, so that means omega is equal to 93.8 radians per second. Now I also know that because it's a sphere, the moment of inertia equation for a sphere is 2mr squared over 5. And again, look at your formula sheet and you'll find that equation. Okay, now the question is asking me for a ratio. It says calculate the ratio of the rotational kinetic energy to the translational kinetic energy. So anytime a question asks you to find a ratio, okay, that means you're dividing two numbers. Okay, the ratio of the rotational kinetic energy. Okay, so let's see, Ke rotational to the linear kinetic energy. Okay, so basically the question is asking me to find what is this number divided by this number. Right, that's what a ratio is. It's two numbers being divided. Okay, well, rotational kinetic energy is 1/2 I omega squared, and linear kinetic energy is 1/2 mv squared. Okay, so how can I find this ratio? Well, if I replace I, if I take my equation for I and I plug in here, then what I see is I have 1/2 times I, okay, which is 2/5 mr squared, times omega squared, divided by 1/2 mv squared. The mass actually cancels out. Okay, so I don't actually need the mass to do this question. 1/2 times 2/5 is 1/5. Okay, so I have 1/5 times r squared omega squared divided by 1/2 v squared. And then all I need to do from there is plug in all of the numbers. Okay, so I have 1/5, so 1 divided by 5, okay, which is 0.2. I multiply by the radius squared. Please don't forget to convert. Okay, this needs to be converted to meters, and so that would be 0.0514 squared. Okay, times omega squared, so times 93.8 squared. Okay, and then so I have 0.2 times 0.0514 squared. I multiply by omega squared, which is 93.8 squared, and then I'm going to divide by 0.5, and then I'm going to divide by v squared, so 54.5 squared. Okay, and so what I get is actually a very small number, and that number is 0.00313. Okay, and that is the answer to that question. Okay, and so this is just giving you an idea of number one, how to calculate rotational kinetic energy, which is something that you need to be able to do, but also how would you actually use moment of inertia to do other calculations. Okay, and so hopefully after watching this video, you have an idea of how to calculate moment of inertia for individual point masses with mr squared, or for bigger geometrical objects, in which case I would refer back to the OnRamps formula sheet. If you have a combination of those two, then what you would need to do is you would need to add the two together. Okay, so for example, in this situation, we have a baseball, right? And the baseball you can treat like a sphere. And so I would be 2mr squared over 5. What would happen to the moment of inertia if you like stuck a piece of gum to it? Well, a piece of gum is like a point mass. Okay, and so what would happen is it would be 2mr squared over 5 plus mr squared for the piece of gum. Okay, and so anytime you have multiple masses, you basically find the moment of inertia for each one and you add all the pieces together. Okay, and so hopefully after watching this video, you have an idea of how to calculate moment of inertia, and you also have an idea of how to calculate rotational kinetic energy. Okay, so as always, please let me know if you have any questions, and I will see you guys in the next video.